magnetic fields and magnetic forces. So we're going to start this by thinking about a bar magnet. A bar magnet is just a regular old piece of metal that is magnetized. You've probably encountered them before in your life. There are things that stick to refrigerators and things like that. A bar magnet, and we're not going to explain exactly why this is, but a bar magnet has a north pole and a south pole. In fact, every magnet has a north pole and a south pole. Can't get away from that. It's a fact of life in the universe. We're going to imagine that around every bar magnet there is a magnetic field, and the magnetic field is going to emanate from the north pole and go into the south pole. So those magnetic field lines, which are analogous to electric field lines, but they're different, they're analogous but different, they go out of the north pole and into the south pole, and they have a pattern like so, like what I've drawn. Now, let's switch gears a little bit. The ultimate source, the ultimate cause of magnetic fields are moving electric charges. Now that seems kind of strange. I just showed you a bar magnet, and I drew a magnetic field around it. There's a magnetic field around a bar magnet. And we didn't mention electric charges at all. So what's the connection here? I've told you that magnetic fields are caused by moving charges, moving electric charges, and yet bar magnets create magnetic fields. Well, the link is, inside of a bar magnet, there are moving charges. You can't see them. But there are little electrons, and they're whirring around. And every little electron that's moving around creates a tiny little magnetic field. And all those electrons inside the bar magnet, they create magnetic fields which add together to make one big magnetic field around the bar magnet. Okay. Another place that we can go with this is, okay, so a moving electric charge creates a magnetic field. Well, where else have we seen a moving electric charge? Current. A moving electric charge, by definition, is a current. So, moving electric charges cause magnetic fields, so currents cause magnetic fields. We can draw a picture of that. I'll draw it right now. So if we have a current going this way, we can draw the magnetic field going like so. Now, how do I know that? Well, there is a rule that tells us the direction of a magnetic field around a current. It's a right-hand rule. So you take your right hand and you point your thumb in the direction of the current. And that's the current that, as we normally think about it, the direction that positive charge would flow. So if we have a current flowing in the direction of your thumb, and we want to know about the magnetic field at a location, what you do is you put the tips of your fingers at the location that you're considering. Okay? Then you turn your fingers in towards the palm. If you start to turn your fingers towards the palm, that will tell you the direction of the magnetic field. So let's try that a couple times. Now let's consider something called a solenoid. A solenoid is just a bunch of loops of wire, and they're arranged in such a way as to form a cylinder. And the outside of the cylinder is the coil of wires. So I'll draw a picture of that right now. Let's think about what the magnetic field would be like inside of a solenoid when there is current running through that wire that's looped on the outside. So we're going to consider a solenoid. I'm going to do a sort of a cutaway view of that. Let's see what would happen if we have current flowing into the page on the top layer of the solenoid and current flowing out of the page on the bottom side of the solenoid. If we have that, well, let's see. Let's think about the piece of wire all the way on the left at the top. And we'll use our right-hand rule to figure out what the magnetic field would be like inside the solenoid. So we point our thumb in the direction of the current, and then we put our fingers at the location of interest. And we're interested on the inside of the solenoid, so I'll put my fingers there. And if I start to curl my fingers towards my palm, you can see they point to the right. So that little tiny wire, that one wire in the solenoid, is creating a magnetic field inside the solenoid that moves to the right, that points to the right. And if we did that for every single wire on the top of the solenoid, we would always get a magnetic field inside the solenoid that points to the right. Okay, so we got a bunch of magnetic fields pointing to the right, courtesy of the top layer, the top side. Let's think about the bottom side. So we do the same thing. Point your finger, or excuse me, point your thumb in the direction of the current. Do that. Put your fingers at the location of interest. Start to curl your fingers towards your palm, and that tells you the direction of the magnetic field from that wire. So the wire on the bottom, all the way to the left, is creating a magnetic field to the right, inside of that solenoid. And every single wire on the bottom is creating a magnetic field that points to the right, inside the solenoid. So, all of the wires are creating a magnetic field that points to the right, inside of the solenoid. So we can draw the magnetic field lines inside the solenoid. They all point to the right. Now, we won't go through the method to figure out the magnetic field outside of the solenoid. I will just draw it. But, if you notice, there's a big similarity between the magnetic field created by the solenoid and the magnetic field around a bar magnet. They look very, very similar. And in fact, a solenoid, the magnetic field outside of a solenoid, acts like a bar magnet, or acts like the magnetic field around a bar magnet. Okay, so let's start thinking about force. If you put a wire that carries a current inside of an external magnetic field, that wire will feel a force. And in class we did an experiment that showed this. But for now, we're just going to call that the magnetic force on the wire. Now the reason for it is because, so there's an external magnetic field, and then there's a current carrying wire. The current carrying wire also creates another magnetic field. It's the interaction between those two magnetic fields, the magnetic field that's external and the magnetic field created by the wire. The interaction between those two is what causes the force on the wire. Now, you might ask, well, what's the direction of the force? Well, we figure that out using another right-hand rule. And the way you do it is you point your fingers in the direction of whatever current you have. You point your palm in the direction of the magnetic field, and then your thumb tells you the direction of the force on the wire. So let's try a couple examples of that. Also, keep in mind that the diagram in your notes may not correspond to the right-hand rule that I just described. There are many types of right-hand rules. There are many ways of explaining it. If you look on the internet and look up right-hand rule, you'll get all kinds of results. I've described the one that I use, and the one that I will use during class, and the one that I will expect you to use on a quiz or a test. It works the same as any of the others, but it's the one that I use. So once we have the direction of the magnetic force on a wire in a field, we might want to know the magnitude of that force. This is the equation for it. The magnitude of the magnetic force on a wire is equal to ILB sine theta. The I is the current through the wire, measured in amps. The L is the length of the wire that's in the magnetic field, measured in meters. B is the strength of the magnetic field, measured in Tesla. And theta is the angle between the current and the magnetic field. Now you have to memorize all those, you have to know what all of those letters mean in that equation, and you have to know all of the units, and you have to be comfortable with that. And this equation can also be used to define the magnitude of a magnetic field. If we just move around the equation, solve for B, the magnetic field strength, we get an equation B is equal to F over IL sine theta. That's one way that we can define or figure out the magnitude of the magnetic field. Okay, so let's do an example similar to the one in your notes. So we've got a North Pole and a South Pole. We've got a wire running through it. We've got a resistor of 5.5 ohms in there, and we've got a battery providing 24 volts to this circuit. We're told that the strength of the magnetic field within that gap is 1.9 Tesla. So, let's see. We need to know, if we're going to find the magnitude and direction of the force on the wire, we want to know what F is. We want to use F is equal to ILB sine theta. We got to figure out the current. We have to know the magnetic field, we have to know the length of the current carrying wire that sits in the field, and we have to know sine theta. Well, B, we're told, is 1.9 Tesla. Okay. L, that's the length of the wire that's within the field, that's the 7.5 centimeters. I, we'll come back to I. Sine theta, well, let's see, let's draw this picture. The direction of the magnetic field, well, magnetic fields go from north to south, and so it goes like so. The current. Okay. Well, the current we can figure out because we know the battery voltage supplied in the circuit. We know the resistance in the circuit, so we can use V equals IR to solve for the current magnitude. Now the direction, well, current always flows from the long side of the battery, the positive terminal, to the short side of the battery, the negative terminal. So that means in this diagram, the current and the magnetic field are perpendicular to each other. In other words, theta, the angle between the magnetic field and the current, is 90 degrees. Well, there you go. Now we can find the force, the magnitude of the force using the equation, and there you go, 0.62 newtons. Now, what about the direction? Well, in this picture, we use the right-hand rule. Point your fingers in the direction of the current, point your palm in the direction of the magnetic field, and then your thumb will tell you the direction of the force. So in this case, the force is up out of the page. In fact, say out of the page. Don't say up. Up can be confusing. Up might mean towards the top of the page, might mean towards the ceiling, whatever. It depends on what you mean. But if you say out of the page, that cannot be misconstrued. Okay, so as I said before, a moving charge creates a magnetic field. It doesn't have to be a whole bunch of charges in a current. It can be just one charge. So you could have one isolated charge moving, and that one isolated charge will create a magnetic field. If you have a moving charge, and if it moves through an external magnetic field, so if there's already a magnetic field there and a moving charge moves through it, the magnetic field created by the moving charge and that external magnetic field will interact. And when they interact, it will cause a force on the moving charge. So what we get, the result of that, is that a moving charge in a magnetic field will experience a force. That's because the two fields are interacting. Now, how much force? Well, we have an equation for that. The force experienced by a moving charge in a magnetic field is equal to QVB sine theta. The Q stands for the magnitude of the electric charge. V stands for the velocity of the electric charge. Well, the magnitude of the velocity of the electric charge. B stands for the magnitude of the magnetic field. And theta is the angle between the velocity of the charge and the magnetic field that the charge is moving through. All right. That gives us the magnitude. We still need to figure out what the direction is. Well, if we want to know direction and we're dealing with magnetic fields, we're probably going to use a right-hand rule. There is another right-hand rule for this. To figure out the direction of the force, you point your fingers in the direction of the velocity of the charge. You point the palm of your hand in the direction of the magnetic field, and then your thumb will point in the direction that the force on a positive charge would be. Okay, so the thumb points in the direction of the force on a positive charge. If you have a negative charge, you have to flip your answer. So if you have a negative charge, you have to, at the end, flip the force. The force is in the opposite direction as what's given by the right-hand rule. I know that can get frustrating. I wish I could rewrite the rules of the universe to make it easier, but they don't let me. I'm sorry. But let's do a couple examples. So, the first one. Let's say we have a positive charge, and it's moving to the right on the page. And then we have a magnetic field into the page. Okay, so we got those things. We use the right-hand rule. We point our finger in the direction of the velocity of the charge. We point our palm in the direction of the magnetic field. If you do that, your thumb will point towards the top of the page. We have a positive charge. Our thumb is pointing towards the top of the page. The thumb then tells us the direction of the force on a positive charge. So this positive charge will feel a force towards the top of the page. Okay, not so bad. Let's try another one. Let's say we have a positive charge moving towards the bottom of the page. Then let's say we have a magnetic field pointing out of the page. To figure out the direction of the force, we point our fingers in the direction of the velocity. You point your palm in the direction of the magnetic field, and then your thumb will point in the direction of the force on a positive charge. So a positive charge would feel a force to the left of the page. And we have a positive charge, so there we go. Okay, let's try another one. Let's say we have a positive charge, and again, it's moving towards the bottom of the page. We have a magnetic field pointing to the right. Take your fingers, point them in the direction of the velocity. Take your palm, make sure it points in the direction of the magnetic field, and then your thumb will point in the direction of the force on a positive charge. In this case, out of the page. Okay. Now, that's a lot of positive charges. Let's try a negative one. Let's say we have a negative charge moving to the right. Let's say we have a magnetic field pointing towards the bottom of the page. We do the right-hand rule just like before. Point our fingers in the direction of the velocity. Point your palm in the direction of the magnetic field, and then your thumb will point in the direction of the force on a positive charge. Here we have a negative charge, so at the end we have to flip it. A positive charge would feel a force into the page, so a negative charge will feel a force out of the page. Alright, let's try a numerical example. So let's say we have a proton, and that proton is moving at 90% the speed of light. As it moves, its velocity makes an angle of 60 degrees with respect to the magnetic field. Now, the magnetic field, we're told, has a magnitude of 0.25 Tesla. And we want to find the force on the proton and the acceleration of the proton. And I'll give you two other numbers. The charge of the charge of a proton is 1.60 times 10 to the negative 19 coulombs, and the mass of a proton is 1.67 times 10 to the negative 27 kilograms. Also, the speed of light, 3.00 times 10 to the 8 meters per second. Okay. So, if we want to know the force on the proton, well, we have an equation to give us the magnitude of that. F equals QVB sine theta. We know Q, we know V, we know B, we know sine theta. So you plug it in, you figure out the force, there you go. Now what about the acceleration? Well, I know the force now. I want to get to the acceleration. The way to get from force to acceleration, from one to the other, almost always, if you're talking about one object's force and one object's acceleration, the way to link those two is Newton's second law. Doesn't matter that we've entered the realm of electromagnetism and things are acting crazy and there's protons and everything's moving really fast. Newton's second law still links force on an object and the acceleration of an object. So we use Newton's law to find the acceleration. Okay. Now what if we change this to an electron? Let's try that out. What would change? Well, if it's still moving as fast, and changing it to an electron doesn't change the external magnetic field, the only thing that's different about an electron is that it has a different charge, it's negative, and it has a different mass. It's much lighter than the proton. So, the calculation would change because Q would be negative, and the mass would change, so that would change the acceleration. So let's go through that. Now there is an extra negative sign. What does that negative sign mean? Well, it's showing up in our magnitude equation. So magnitude, that doesn't have a positive or a negative associated with it. What does that negative sign mean? Well, negative signs, almost always, if you ever encounter a negative sign, what it almost always means is direction, or it refers to a direction. Especially if you're talking about vectors, it will refer to a direction. Here we're talking about force, so if we have a negative force, that means it's in the opposite direction. But you already knew that. You know that if you have a positive charge and you figure out the direction of the force, the direction of that force is going to be opposite of that of a negative charge. So it's telling you what you already know.